Okay, welcome back to our next lecture on relativistic mechanics. In our last lecture, we worked on the idea of a decaying particle in a center of mass frame. And that is sort of captured by this image here, where this blue particle is the particle that's decaying, the parent particle, and it decays into these two green child particles, which are not necessarily the same mass, right? These two particles may have different masses. Mass A and mass B, and the original particle has this mass capital M. And last lesson we were able to calculate the magnitude of the three momentum of the child particles in this center of mass frames, all in terms of just the original and final masses, which was a really nice formula. And we were able to figure out what might be obvious, but that the mass of the two children particles must be less than the mass of the parent particle in order for this this process to make any sense. So that was interesting. And this was done in the center of mass frame, which is characterized by a four momentum. This capital P is the four momentum of the parent particle in the center of mass frame, where the parent particle is motionless. And that motionlessness is reflected by the absence of what would be these three components of the four momentum would be the three momentum. And since it's motionless and the three momentum is defined by gamma times the mass, the invariant mass of the particle, times its three velocity, right? If that velocity is zero, of course, this part is zero, right? And that's what we're saying. So this is how we really are defining the fact that we are in the center of mass frames, is we are setting these three velocities to zero, which is really simple. We say it two ways. We say we're in the frame where the velocity is zero, but another way of saying it is we, the observer of this whole affair, is moving along with the particle. And this is one of those cases, physics, we talk a lot about being the observer. And relativity was the first place where, well, it's a place where this really becomes important, is who's observing and what are they measuring. And this is a big deal in quantum mechanics too, but for completely different reasons. So it's a fascinating thing, but getting used to being an observer and interpreting things as an observer is just a huge part of understanding relativistic mechanics. But right now we're moving along with the particle. And we solved these two things, and we had, of course, the conservation of energy, which is the first component of the four vector, and then the conservation of momentum. We did this last time. So now we are going to explore what this looks like in the moving frame, meaning, so it's interesting because I say the moving frame, but what I want to mean is the frame where this particle, the parent particle, has an initial momentum, and I want that initial momentum to be into the direction from left to right. So the particle is now moving, but the moving frame I need to boost to is the frame of a laboratory where we're standing still and the particle is moving from left to right. So my laboratory relative to this center of mass frame is actually moving from right to left with a velocity v, a magnitude v, and a vector velocity of minus v. So minus v is going to basically be the speed of my laboratory moving to the left, which is another way of saying that in my laboratory, this particle looks like it's moving to the right with a speed of v. And so now I'm interested in that frame. So let's start telling that story. Now the good news is we've already solved the problem in one frame of reference. We don't need to start fresh in another frame of reference. We just need to take our solution from one frame and transform it to the other. And this is a ubiquitous step that happens in special relativity, and I'm going to show you my favorite way of doing it. So the first thing to do is make sure we have all of the four momentum vectors relevant to the problem. We already showed you the four momentum vector relevant to the parent particle, But the two daughter particles, or children particles, A and B, they have their own 4 momentum vectors, and we need to write those down too. So they're not hard to write down. So the 4 momentum of the A particle is just the total energy of the A particle in the time-like slot. And then the total momentum, the 3 momentum magnitude of PA multiplied by sine theta, it's going to decay in some direction. We don't know what direction this particle is going to decay in. It could decay like this, could decay like this. You do know that the two particles are going to decay back to back because of conservation of momentum, which we discussed last time, but you don't know what direction it's going to decay in. So that's out of our control. What is in our control, however, is this direction z, because that's going to be the direction that we're going to transform to, where the particle is moving with a velocity v. So that velocity v that we're transforming to will be aligned in a direction that we're going to call the z-axis. And then perpendicular from the z-axis, we're going to have an x-axis, and we'll suppress the y-axis as coming in and out of the plane, and we'll assume that this decay happens in the zx plane. That's easy enough to do. But we never know what theta, what angle this particle is going to split into. That's not in our control. That's a process that's buried deep into the physics of this particle's substructure, right? Well, not even substructure, really, because if it's a muon, as far as we know, decays, but it has no substructure. So let's imagine it being, you know, a quark, not a quark, some sort of hadron or meson that will decay. And the physics of this decay, everything that goes on in here that leads to its splitting into these two particles, all that physics is quantum field theory, quantum chromodynamics, quantum electrodynamics, or the quantum theory of the quantum field theory of the weak interaction. And we don't know anything about that, but we do know that when all of the magic is done inside here, what has to result in the end is the physics we're talking about now. So the physics we're talking about now is often called on shell, right? The ultimate answer has to be on shell. And we'll talk about what that literally means a little bit later, but the point is that we are burying all of the unknown physics that makes this particle decay inside a black box. We're giving the particle some sort of lifetime, tau, and that lifetime is just, we expect this particle to decay, you know, on the order of this lifetime. And that's as much as we need to know for the relativistic mechanics. So but we do know that in the center of mass frame, there will be an angle theta of its dissolution. And one of the things we're going to ask is, hey, in the moving frame, what does that angle look like? What does that angle look like if I'm in the lab and the particle's zipping by? Is it the same theta? Is it a different theta? And how is the angle that is measured in the lab related to the angle that would be measured if you were moving along with the particle? It's a fair question. But we want to build all of our 4 vectors. We already built the 4 vector for the parent particle. It was pretty trivial. And now we're going to build the 4 vector for the child particle. So the total momentum, the sine of this angle, I went into this digression about this angle. Well, the sine of that angle is obviously going to be the x component. The cosine of that angle is going to give you the component in the z direction. And for the other particle, the B particle, the total energy of the B particle, and it's just equal and opposite, right, to the A particle. So I don't even have a total momentum of the B particle because I know that it's the same as the A particle. And I think in the last lesson, if I remember right, this was just gone and we just wrote it as A, right, because it's just a single number. But I'm going to leave it as P sub A for now because that's how I did all the math. So now we have the 3 relevant 4 momentum vectors, which is basically the problem totally solved in the center mass frame. We have the child particle 1, child particle 2, and over here we had the parent particle. So now we need to do the Lorentz transformation. So how do we do the Lorentz transformation? And this is the way that I want to teach the Lorentz transformation. Now, we did a whole lesson on the Lorentz transformation in our section on QED prerequisites. So this is a rehash of that. But there's these two matrices. I pulled them off of Wikipedia, so you can find them there, no trouble. And this is the Lorentz transformation of a general boost, a boost in an arbitrary direction, where the three components of the boost are beta x, beta y, and beta z. And you'll see, I'll use this black one up here, because I just like the darker color here. But this beta x is the component of the boost in the x direction, the component of the boost in the y direction. Beta z is the component of the boost in the z direction. And then you have gamma. Now remember, gamma equals 1 over the square root of 1 minus beta squared. But it's not beta x, it's not beta y, it's not beta z, it's the total beta, right? So it's the magnitude of the overall velocity of the boost, right? And of course, this gamma usually affects this time component, the total energy, which has apparently less of a care about what direction it's in, more about the overall size of the boost is what's important to that particular part of the transformation, I suppose. But you'll notice that, so in this version of the matrix, you put in each of the components appropriately. There's all these gamma factors. The diagonal has all of these ones plus these gammas. And you build this matrix, you multiply everything by the relevant 4 vector, and you end up with the transformed 4 vector. It's very simple. Now the other form of the matrix is just, it's algebraically it's different, right? The top row and the first column are actually the same, but the algebraic structure of the guts you can see is different. Here you have a gamma squared over 1 plus gamma, right? Gamma squared over 1 plus gamma there. And then here you have gamma minus 1, which looks a lot simpler, but you end up having a beta squared in the bottom, where that's the beta of the total transformation, the beta related to the magnitude v, overall magnitude of the velocity of the boost, right? And then you have bx and by as a factor in both of them. So algebraically, these are very, very different. And this is the matrix, the top one, that's the one I learned when I studied the subject. I think this is the one that's in legendary electromagnetism textbook called Jackson. I'm quite sure this is the one that's in there. This one I found I think it was on Wikipedia or something very similar. And I was a little surprised. I had to spend some time to convince myself that algebraically this is all the same. But anyway, we got to fill this matrix out for our circumstance. And in our circumstance, remember, we are now going to boost, we want the particle to have a velocity along the z-axis that's v. So ultimately, our total beta is just going to be beta z, which is going to be minus v over c. Now, in the next lesson, we're going to do units, and we're going to see how c equals 1. But the point is this beta is going to be, we're boosting from right to left in order to get the particle to move from left to right. But right now, beta and beta z are the same. We have beta x equals 0, beta y equals 0. So those two are 0. So beta and beta z are the same because we're only boosting in the z direction. And there's probably not too many cases in this field where you really need to have boosts in arbitrary directions, right? That would be a pretty advanced problem. So we can take this matrix, either one of these, and fill out everything correctly. So what would it look like? Well, beta x is 0, beta y is 0, and beta z equals beta, right? Again, 0, 0, and beta z is 0. Everywhere where I see a beta x or a beta y, those terms are going to be 0. So this is 0, 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 and this is 0. So all those are 0. So then well, actually, this is 0, this is 0 too. So that just leaves the 1 and the 1. And this becomes beta, this lower right-hand slot here, that becomes beta. So now, if I do the same thing to the matrix down below, because they're both should be the same, I basically get the same effect. These two guys go away, these go away. All of the off-diagonal terms end up going away, right? This one here and this one here. And all that's left and is, well, then this goes away for beta x, this goes away because of beta y. But now beta z and beta are the same, so that becomes 1, right? And then you have 1 minus 1 plus gamma. So this whole thing becomes gamma right here. And of course, this is gamma up in the upper left. But if you look at this version, it's not evident at all to me that this term here, 1 plus gamma squared over 1 plus gamma times beta squared, that's got to equal gamma, right? These two matrices are both Lorentz transformations. They're both algebraic expressions of the same thing. These two have to be the same. And I actually spent some time convincing myself that they were. And again, you end up in this sort of algebra zone where you have to kind of do a bunch of algebra to realize, okay, yeah, this thing here actually simplifies to gamma. And I got to say, this second matrix really wins in convenience because it just gives you gamma right away. Here, you have to either do the calculation or convince yourself, or you never notice, and you just put in the numbers, and you never realize that you've just recalculated gamma using an extra step. So because I had to go through it, maybe it's obvious to you guys, I don't know, but it wasn't obvious to me. So, but I'm going to drag you through it. So we write down gamma as 1 over 1 minus beta squared. Remember, this is the overall beta. So I'm going to solve for beta in terms of gamma. Not too hard to do. Square both sides, multiply both sides by 1 minus beta, and then I'm just trying to solve for beta squared here, which isn't tough. So I get beta squared is 1 minus gamma squared over minus gamma squared, and ultimately I write beta squared is gamma squared minus 1 over gamma squared. Then go ahead and factor this in anticipation of a cancellation, and I get gamma minus 1, gamma plus 1 over gamma squared. So then I say, okay, I'm looking at this thing, right? This is the thing that I have to convince myself ultimately equals gamma, right? I have to convince myself of that, right? And I do my substitution. I substitute this beta squared, right, with the thing I just calculated. And then, of course, that cancels with that. This cancels with this. And I'm left with, look at it, 1 plus gamma minus 1, which equals gamma. So it's true, right? But what is useful is this expression here. That's the thing to keep in mind, I guess. So there's always this weird algebra in relativistic mechanics that you just got to get used to. The more you do it, the more you recognize, oh, I remember that. Got to solve for beta squared and all this stuff. So anyway, this is just proof that those two matrices are in fact the same. All right, so back to these matrices, you just pick the one you want, and when you do that, you end up with this expression. Notice when I was doing this, when I wrote this out for everybody, I left it this way thinking, I'm going to have to work on that. And then I actually worked on it, and eventually I substitute for gamma. I substitute all this for gamma. All right, so now I have my two matrices. I have my my 3 4 vectors, really. I have the 2 daughter particles and the parent particle, and I have my Lorentz transformation. Now I'm going to make some substitutions, right? I'm going to substitute for EA gamma MA, right? This is a little fact that you just got to always keep in your mind, that you take the invariant mass, multiply by the gamma factor, and that is the total energy of the particle. We're going to talk a little more about that in the next lesson. I found a really, really great source of material for some inspiring history and intuition about that. So we'll talk more about that. And then also we have to remember that the 3 momentum is basically the literal classical 3 momentum multiplied by this gamma factor, right? So I can make these substitutions, right? I can substitute this stuff right in here, right, for PA, and then substitute this stuff in for EA, and I'll do that in a moment. But first, let's do the Lorentz transformation times the first of the 2 children particles. And this is now matrix multiplication, right? This is straight matrix multiplication. So I take, it's EA times gamma, which lands here, and then it's minus gamma beta times PA cosine theta, which lands there. So that's the first term. PA sine theta is just multiplied by 1, so it just goes straight. Of course, that's the piece of the momentum that's perpendicular to the motion of the boost, so it's not changed. And then it's EA times minus gamma beta, that lands here, and 1 plus gamma squared over 1 plus gamma beta squared times PA cosine theta, which lands over here. So this now is the transformed the transformed 4 vector. So I now have the solution in the transformed frame. I don't have to, all I had to do is take a solution from a frame that was easy to solve in and transform it, and now I've got this messy thing, but it's the answer because the transformation is always right. And I think this is the point where I said, okay, what is this? And I realized, hey, that's just gamma. So I make one more simplification, and I take all of this and I turn it into just ultimately just gamma. But I also make a few other substitutions, right? I'm going to substitute these things into here, where I see the momentum of the child particle. I'm going to substitute gamma MAV, right? So I'm going to put that in here. And where I see the total energy of the child particle, I'm going to substitute gamma MA in a moment. So now that I have this, I'm going to ask my question, okay, well, what does the angle look like in the lab frame? And, well, the angle is going to be, in the lab frame, it's just going to be the tangent of the angle is going to be the x component divided by the z component. That will be the tangent of the angle in the lab frame. And in the lab frame, I'll call it theta star. I found a paper that liked to use stars for the transform frame. And I've never used a star for the transform frame before, so I thought I'd give it a try. See how that notation feels for me. So I'm going to take this and divide it by this, and what we do is we end up with this expression. Now notice there's no momentums anymore because I've substituted gamma m VA for momentum, gamma m VA for momentum, and likewise for energy, I substituted gamma MA for this energy. So there was this EA term here that got substituted by gamma MA. So this EA goes to gamma MA, and that ends up there. And this PA gets gamma MA VA, and that goes down here. Likewise, gamma MA VA gets substituted for the X component part. And then it's just a bunch of divisions, right? You know, this cancels. Let's see if I can do the cancellation. This gamma cancels here. The MAs cancel. That's kind of interesting that the mass all cancels out. And then I end up with this expression. And then just to put it into a form that's kind of suggestive of a tangent, I divide top and bottom by VA. So I get a VA here, and that goes away. And I pull out a gamma. I can pull out this gamma. So after doing all that, I'm left with this really nice expression for the tangent of the angle in the lab frame is related to the sine of the angle in the center of mass frame and the cosine of the angle in the center of mass frame. And then this is the boost that we have to do. And this is the velocity of the total velocity of the child particle in the center of mass frame. So everything on this side is from the center of mass frame. And and even the boost is sort of from the center of mass frame. But now we have to remember that beta is equal to the velocity of the parent particle with a minus sign. Because remember, the boost goes from right to left, and we're defining positive as left to right. So beta is going to be minus v of the parent particle. So this could actually be v parent over v child plus cosine theta. And sure enough, if we're in the center of mass frame, then v is equal to 0, gamma is equal to 1, and this term goes away, and you get tan theta equals sine theta over cosine theta. So the check works out, it limits correctly, and now we have this beautiful expression. And in the spirit of keeping these lessons now down to a half an hour, in our next lesson we will actually apply this to an actual particle that's actually decaying. We'll pick some elementary particle decay process, and we'll do these calculations, and we'll kind of study what this looks like a little bit. And in that process, we'll learn a little bit about the units that we want to use, and get that square. We'll stick to the units that are somewhat typical in particle physics, and then proceed. And then we'll go back and we'll kind of go back to some of the original material that discussed these things, and we'll get a bit of a historical and a little bit of a almost philosophical perspective about how that all works. And then we'll just keep going into more sophisticated problems involving collisions and decays of various processes. Okay, see you next time.